Okay. Good morning, everybody. Welcome to NAPE, the Nigerian Association of Petroleum Explorationists, August Technical and Business Meeting, sponsored by Total Exploration and Production Nigeria Limited. It's my pleasure to be your host again. My name is Abdulateef Amodu, the Publicity Secretary for NAPE. Today we'll be having a very exciting technical presentation from Total, who are also the sponsors. The presentation is titled The Geological Facies Modeling, Why Should We Care? I believe this is going to be a very exciting technical presentation as usual, and I hope everybody benefits from it, because if there's any time in which we want to get the most from the surface, it is this time. Without much ado, it's my honor and pleasure to invite, as usual, my president-elect. I'll call her the person who is going to be ushering in the virtual and digital NAPE. Having said that, it's my honor to request the presence and participation of the president-elect, Mrs. Patricia Ochobo. My president-elect, are you there, ma?
Yes, I'm here. Thank you.
No problem, ma. Over to you, ma.
Okay. Good morning, ladies and gentlemen. I really want to thank you all for taking time out to join this meeting. And I believe we are all going to sip from the well of knowledge that Total has carefully provided for us today. I will like to I would like to talk about, welcome the speaker for today. His name is Mr. Eric Tawile, and he is a geophysics and geology manager for Total. Mr. Abiodun Adesanya is our chairman for today. He will do a full introduction of Mr. Eric. But let me introduce Mr. Adesanya to you. He went to Ife and graduated in 1983. I have stories about that, but not for today. And he joined the United Geophysics, UGNL, after his national service as a trainee seismologist. And he already has shown signs of greatness because he actually rose to become the party chief, and that is not a small feat at all. He left UGNL in 1990 and joined Elf Petroleum. Elf Petroleum is the grandfather of Total. For those who do not know, at a time it was Elf Petroleum, then it became a Total Fina, Elf, and the company is now Total. And I believe we chose him because he has a good background of this information. He's a trainer of trainers. He's an astute business person, so he understands both the academic and the business aspects of what we are going to be talking about today. I shall not waste your time, but I will just call to the podium Mr. Abiodun Adesanya. Please give him a warm NAPE welcome. Back to you.
Ladies and gentlemen, I believe I'm on now. Yeah. Good morning. It's a pleasure. Let me get my video up and running. It's my pleasure to be with you once again. I was just throwing banters with the publicity secretary and the president earlier on when I said that this week has been quite an intense one. There's still another event coming up very soon, I believe tomorrow. So we've had quite a lot of very important, very exciting programs in a week, and that's a feat. Thank you very much, Pat, for the brief introduction. Pat and I graduated together from Ife, so she knows what she's saying when she said it's another story for another day. Without much ado, we have a very exciting topic to discuss today, and there's no any other better person to take us through that than the the Geology and Geophysics Manager for Total. His name is Eric Tawile. Eric, bonjour and bienvenue à NAPE. This is our forum of equivalent to the AAPG. I'm sure you're familiar. So I'm just going to quickly go through the biodata for Eric. Eric graduated from in 2009 with an engineering degree from the School of Mines in Nancy, France, and then from Imperial College London with an MSc in Petroleum Geosciences in 2010. He was hired by Total in November of 2010. He held his first position in Paris as a reservoir geologist in reservoir characterization and modeling department. His major roles included providing support to subsurface study teams, carrying out research and development, and giving training in reservoir modeling and uncertainty management. During this time, he participated in the development of in-house tools dedicated to trend combinations in geological modeling and uncertainties evaluations. This development led him to be associated as co-inventor in 6 patents. In December 2013, he was appointed to a reservoir geologist position in Doha, Qatar, working on field development subjects mainly focused on carbonate environments. Within a multidisciplinary team, he participated in the development of the first in-house operational workflow, linking multi-realization outputs of a stochastic inversion in geological modeling and reservoir model history matching, thus achieving full integration from seismic to reservoir simulation in a multi-realization workflow. In addition, he developed a specific workflow for the integration of long horizontal wells in geological models to ensure consistency between well placement and geological layering. In Qatar, he also worked in the reservoir monitoring team, where he developed with his well performance colleagues a probabilistic approach to identifying workover candidates of electrical submersible pumps ESP-equipped wells. In summer of 2017, Eric moved to Total Exploration and Production Nigeria as Geology and Geophysics Manager of the Egina Field Asset Team. The first oil was in December 2018 and is currently producing at Plateau. Eric is now addressing the field challenges with his team to ensuring sustainable production from the reservoirs in the years ahead. He is married with children. Professional interests. Main professional interest is uncertainty management in E&P cycles, geological reservoir modeling, integration of seismic constraints in geological modeling, seismic inversion, holistic development approaches. His hobbies: free and scuba diving, geopolitics, cooking. The geopolitics one, I don't know whether it covers Nigeria or not. He's been involved in several publications, most of which are directed towards what we're going to be hearing today. I will just go through a few of them. Integrating stochastic seismic inversion and classification results in geological model, a feasibility study of an offshore carbonate reservoir. That's himself and some other authors in 2015. I'll just pick another one. Compromise an innovative method for combining proportion cubes for facies modeling. So everything, like I said, is tuned to what we're going to be listening to today. So without much ado, I bring in Eric Tawile. He's going to be discussing with us today a very important topic, geological facies modeling. Why should we care about that? Why should we care? Ladies and gentlemen, Eric Tawile.
Good morning, everyone. Thank you, Mr. Chairman. Thank you, President, for the warm welcome. Thanks for the introduction, and I'm really delighted today to be participating with you to this NAPE technical meeting. Of course, we would have preferred to be gathered all together for the meeting, but with the current circumstances, we'll have to go opportunity to present. I'll start sharing my screen with you. So I hope this will work as it's supposed to. So while this is coming up, let me start the introduction by talking to you about weather forecasts. So, you know, well, we usually take our smartphones or look at the TV just after the news. Usually you have the weather forecast coming up for the next 1 day and then 2 days, 3 days, and then they tell you towards the end of the week is going to be, but it's relatively uncertain on how this is going to go. And all of you are aware that to do the forecasting, weather agencies around the world basically send up satellites, put up radar stations, and then some other tools, local tools, just to measure pressure in the atmosphere or something else to make sure that they have enough data to integrate and try to make a forecast of what the weather would be like in the next few days. And I think you're starting to understand the link I'm trying to make here between weather forecasting and the topic that we'll be discussing today is, well, the reservoir modeling aspect, where we are using reservoir models to do forecasts for different reasons, of course, but still trying to do forecasts of how the objects and the fields that we are developing will behave in the future. And as you've heard, they basically use tools to make measurements, acquire data, and it's the integration of all that that allows them to predict how the weather would be in the next few days, albeit with some uncertainty, of course. So I hope the slide is now up and running. Latif, I can see you said no presentation yet. Any change on that end? Okay, perfect. So today we're going to talk about geological facies modeling and why we should all care about that. Because, well, in the end, about the facies, right? It's not what we want the model to show us. It's not the facies. It's the results at the end, the forecasts. So today, what we will look at is, well, what do we do with geological reservoir models? What do we do with them? After that, we'll look at the number of techniques comparing facies modeling with petrophysical modeling, and where the petrophysical models are actually inside the model. How are they organized? And you will see that the key to that is the spatial organization. So in the end, we'll look at different techniques to manage facies spatial distribution. We'll talk specifically about the proportion cube and give a few case studies, examples in a few slides to show what this how this can in reservoir models. So let's start with reservoir models. What are they for? So I'll put up the animation so we don't have too much lag. All right, so I have everything on. So what is the reservoir model for? Well, typically what we want to get out of a reservoir model, it's a tool to give us production forecasts, allow us to build development schemes, and basically make decisions. Decisions for our top scale, for reservoir management, and for the top deciders in our companies to be able to make investment, divestment decisions. And of course, the reservoir model outputs, the forecast, the volumes, all of that is only a part of the decision making, but it's a key element for that. So fine, but what do we need to do with that model to reach that stage? Well, you will start by integrating the data that we have. And when we talk about data in geoscience world, we're talking about the seismic data. It's basically our eyes, our own radar, the thing we can use to see what's happening in the subsurface. In addition to that, we have the geology, the ancient and current analogs, outcrops, plus the concepts, all the people that have worked on depositional systems, the physics behind that, how the different depositional units are genetically linked with each other. So this is, I would say, the building blocks of knowledge and concept that we will need to use to make sure that what we're modeling makes sense and it's relatable to the objects that we can see in the world physically. After that, we have the data samples in the subsurface that we actually get to have a look locally and physically of what's happening. And these are the wells, along with all the data that is acquired with them. And is by putting everything together in that melting pot, which is the reservoir model, trying to, after that, history match. So basically make sure the model and what reality is showing us in terms of production, in terms of pressure behavior, in terms of water breakthrough, is actually being reproduced correctly by the model. And in the end, what we're looking for is predictability. To do the geoscience world, to estimate volumes, optimize the developments, look at the uncertainties, and try to have reliable forecasts and development opportunities to maximize field outputs while minimizing risks. Okay, so of course, in addition to that, you need to account for all the uncertainties, because in the geoscience world, you can't have a full picture of the uncertainties. This is something that we manage as the geoscience community, and this is something we live with. So it's a balance between the risk that we are taking and the uncertainties that we have, and the benefits that we can take out of making a given investment here. So that's fine, looking at the reservoir model, but let's have a look at some of the building blocks of that reservoir model, and we're going to count the techniques. So the first aspect of counting the techniques here, we will first look at the techniques related to the Facies modeling aspect. So I've listed some of them here, and you can see there is many techniques. We have the classical ones, the older ones, which is like indicator kriging. You have the I would say more recent one, which were born with the additional computing power, such as multi-point statistics with different types of algorithm, or the pluri-Gaussian simulation, where we can have complex relationships between the different facies compared to a truncated Gaussian simulation, for instance. And of course, we've seen in different forums and presentations, either in the APG, IPTC, EAG, etc., that there is a lot of companies also trying to work on either in-house developments or modified algorithms to address some specific in the carbonate environment where we have diagenesis, scarce modeling, fracture aspects, etc. I'm not covering that here. So you can see there's a whole bunch of techniques here, right? So let's look at petrophysics. What about that? When we look at petrophysical modeling, we basically have two major techniques that we can use today. The first one is kriging, which is, well, I would say a bit out of fashion, so it gives you only a single result. And the second one is the sequential Gaussian simulation, which is typical modeling techniques for continuous property modeling. And that's what we use, I would say, maybe 95% of the time in petrophysical modeling. After that, again, we have some in-house algorithms for very specific topics, but I'm trying to cover here the majority of the fields that we're looking at. So when you look at that and you compare that, you can see that there's much more approaches on Facies. That petrophysics is actually the physical representation, the parameters of your rock properties, and not the facies themselves. The facies is just a description of what kind of rock we are looking at. So why is that? Well, let's look at where, so again, I'll put up the animations. So, all right, so let's do that. Put up the animation so that there is no lag on your side. So what's the model aim today? When we build a model, I mean, okay, for some of us it's a fun thing to do, and I hope we all enjoy that in our daily work. But the aim really is to do prediction. Prediction of what? Volumes in place, yes, that's fine. And production forecasts. Production forecast, why? Basically, it's an input to manage project economics. And in the end, you're basically trying to make, for instance, development of a field, or you would want to know the economics of a single smaller project like drilling a well. So you would want this well to know what's the production forecast of that well. So to do that, what's the input parameters that you need in your model? Well, you need a GRV. So the GRV is basically building a grid, a geocellular grid that will gross, net effective porosities, net effective saturation, formation volume factor, which you would probably get from a reservoir engineer. You would need the permeability field, the horizontal one, the PVT to describe your fluid, etc., etc. And then you would plug all of that into, well, part of that in the static model, and then the rest of that into the dynamic model, and start running. It's not used, it's not observed by any simulation algorithm. So why do we need the Facies scheme? On the bottom left-hand side, you have an example of a Facies model. So you can see a whole bunch of Facies here. And what we will see on the next slide is that the Facies is actually a discrete support of physical properties correctly inside your model. So it's a kind of spatial distribution or a spatial control of the different petrophysical properties inside your model. So here we're looking at an example from turbidites. So at the, let me again run the animation. So okay, so at the top here you can see three different petrophysical petrophysical properties to gross, porosity, and permeability fields. So you can see in the when you're looking at the grid this not arranged by chance. They're not. There is some fairly high contrasts between different areas in the net to gross, porosity, permeability, etc. And when you look at the central image, which is the Facies model, well, we can see that the petrophysical property are highly dependent on the arrangement of the facies. And you can see that these facies, well, they look like geological objects that we can see on outcrops, etc. Here you can see a pair of channels, a small lobe. So the facies model will control the petrophysical spatial distribution and their values. So what do you need to do to get that Facies model right, if that's controlling the petrophysical properties? Well, for one, you need very good eyes. And when we're talking about very good eyes, in our case, in the geoscience world, is usually very good seismic. So invest in your seismic, because the better you see, basically, the less uncertain the large-scale geological objects. The second aspect that is very important is the relevant knowledge that you will apply, and that's the concept. So that's typically facies arrangement inside a given geological objects. For instance, in the turbidite world, we know that in a channel environment, individual channel sequences are a finding upward sequence. So you know that there's a given arrangement of facies inside the channel. So if with the very good eyes, you can map out the channel, with the knowledge, you can know how to populate the better distribute the petrophysical properties inside your model. So that's fine. Let's look at another aspect of the spatial distribution impact. So again, I'll put the animation on. In this slide, you will see two versions of a single model. All right, you will see a V0, version 0 of a model, and then you will see a version 1. And let's have a look at what happened between version 0 and version 1. In this case, we are still looking at turbidite environments, and the yellow are actually the sandy facies, while the green, light green and olive green or dark green facies are rather the shaly facies that you will be looking at. So just take the time yourself to have a compare version 0 with version 1 and at the spatial distribution of the facies between the two. Okay, and I guess you can all see that there's a tremendous change between the two versions. The first one, so what happened? Why did same people that had maybe the knowledge, probably the knowledge actually, and people that try to do the best job they could have done such a difference? Well, the first thing I can say, okay, I have a message. Probably the slide is not up. Latif, is that the case for everyone?
Yes, that's the case for everyone. They can ask that question using the Q&A prompt. And we will take the Q&A after your presentation. Okay, so yeah, what I meant, the presentation, are you all on slide 11? Because I've seen a comment that the slide was not changing on their end. Oh, okay. Okay, I can see someone said they can see the slide. Okay, that's that. Okay, all right, that's fine. Thanks for the feedback for some of you. So what happened here? Well, data.
between the two versions, basically the company acquired a dedicated seismic acquisition to image the reservoir properly, and also ran an adapted processing and imaging work after the acquisition. And that's really one of the fundamental building blocks. I mean, that's, I would say, our eyes is really that first step. The seismic data and the thing we do with it, the processing and the imaging. Secondly is the seismic reservoir characterization. So they've used that data to extract attributes from the seismic to let them know where the facies are located. And finally, well, you need the knowledge, the concept, the people that have the possibility to put all of the available input data. So that's on the seismic end of things, the inversion outputs, the interpretation, and also the well data, the geological knowledge, and try to make a model which makes sense out of that. And you can see here that probably if you ran reservoir simulation between version 1 and version 0, you would probably get very different outputs and also a very different distribution of volumes inside the reservoir. So you would probably not put the development wells in the same place. So it's a very important aspect to know where are your good facies, because that will tell you where are your good petrophysical properties. So you understand now that the key here is spatial distribution. All right. So to manage the spatial distribution aspect, okay. Okay, it's coming up. I'm sorry, I have a small lag on my side now. To manage the spatial distribution, I'm speaking here to the geologists. Well, you have a look at different heterogeneities and the arrangement of facies between themselves on an outcrop, or a modern day analog when you go visit a meandering river, for instance. I mean, the Mississippi is a very nice example of that, analog for wave dominated deltas, for instance. So we do have things that we can study and look at to understand that spatial distribution. So yes, field geology is very nice. This is one of my field works that I had done in the past. So here we're looking at small scale heterogeneities, shale drapings, the genetical relationship between the depositional units, and the grain size distribution in that clastic environment of the small sequences to know how this will impact the distribution of porosity, for instance, inside this massive sand interval that we're looking at. Okay, so that's one thing. We also can have a look at the large scale boundaries and their M-sequence boundaries, erosional surfaces, and the relationship with the surrounding rocks that will be being eroded. Example of a maximum flooding surfaces with that condensed section, and I was walking on that on the field, and it was pretty nice actually seeing that MFS and then trying to follow it around the outcrop. And lastly, you also have knowledge of geometries and the scale of the different objects, because we're working in reservoir models, but it's also very important to tie scale aspects back to what we observe in the field. So we can look at fairway architecture, unitary, and here you can see we have three nice channel sequences. You can see some of the erosional surface of the unitary channels inside these three large-scale fairways. So it's really important to have these scales in mind when we are building our models to make sure that they are relatable to the objects we see in the natural world. Okay. All right. Another small glitch for me. I apologize. Trying to get the slide to move on. Okay, so I think I won the jackpot here. I have a crash of the PowerPoint. I think it's back on. So let me know, everyone, if we're okay on slide 16.
Okay, so slide
Should
16
take a couple
is,
of more seconds to come up.
okay. Is that knowledge of geometries and object scale? Please confirm, Eric.
No, it's the next one.
Okay. So we're waiting for that to come up.
All right, so apologies about that. It's the uncertainty of virtual meetings.
Yeah, it's up now. It's up with a
All
lot
right,
of
so
geometry.
all right, perfect. Okay, so the point here, we looked at very nice outcrop pictures. That's fine, but that won't make a model that by just using what we do as the field geology work. What we need to do is to bridge the gap between the naturalist world of the geologist, looking at outcrops, trying to understand modern and ancient analogs, and the numerical world, which is the grid, the properties that we will be putting inside, and the simulation, dynamic simulations that we will be running to understand that. So here you have two examples. One is turbidite based, the other one is a fluvial environment. And you can see that to do that, you need, as we said, the eyes, you need the knowledge, and you need to integrate the information that you have. So what's at stake of doing that? Why is this Facies spatial distribution so important? As we've said, it's usually the heterogeneities and the reservoir properties are supported by the Facies scheme, all right? So it's the main building blocks that will tell you, okay, this is there, this net to carbon volume in place, which in turn, of course, will impact STOIIPS reserves. Well, STOIIPS, you could tell me, yeah, STOIIP is relatively easy when you're doing, I would say, Explo with very little information. You just get top surface contact, you get the GRV, you get average parameters for that, and you just apply a very simple equation that everyone knows to get average parameters. But when we're talking about development, you would now want to know where to position wells, where are the sweet spots in your reservoir, etc. And you can't use average parameters populating your model to do so because, well, you're not having, I would say, any differences. So you say, let's put the well anywhere, it's the same. And you can translate that equation by making it a sum depending on the different facies that you have, with each facies having its own specific petrophysical parameters. And then these parameters will be scattered according to the facies spatial arrangement inside your model. So in the end, how it will impact is the fluid flow simulation, and hence the reserves that you can get out of it with a specific or at least relevant development scheme that goes with it. All right. So what we want to do as geoscience professionals, we want to avoid volume bias. We want want to make sure that our models have a geological meaning and a geological spatial organization, and basically to convert the information, the knowledge that as geoscientists we have from the field work, from the geology work, from the seismic observations that we have, into a numerical forecast. So let's look at one of the tools that I personally like a lot, and I would recommend to put the efforts in terms of reservoir modeling, is the proportion cube. Why is that? I consider that my best friend. So proportion cubes, I would say, are reliable friends for many reasons. I'll just show a couple of examples before going into the details. So here you will see basically a channel system, 2 channels. And you will see at the topmost part, you have the orange Facies proportion cube. And in the lower part, you will see that you have the Facies simulation result, but the very typical sequential indicator simulation. And at the top, you can see the colors here will represent the probability of occurrence of the facies. In particular, the orange one being more presence at the base and basically disappearing. Again, the proportion cube will not give you a deterministic results. It allows you to go through simulation, and it will represent try to put the facies, the orange facies that you have here, in an arrangement so that it will respect the probabilities that you have given it through the proportion cube. And you can see here, well, you have more orange facies towards the base, and then towards the top, you have less of those. And in the area where it, in the purple here, where it basically has 0 chances of occurring, well, you don't have them. So it's quite a remarkable tool that we can use to control the spatial distribution of facies in a model. So this was a example in okay, this was an example the vertical aspect. I'm looking here at an example which is in 2D, and here you have a map which is representing the different proportions, and you have the yellow facies, so sand proportion distribution, and you can see that yes, you will find that east-west or east east-west trend on that map, with less and less sandy facies towards the east and the southeast. And of course, you can combine that combine 1D and 2D aspects and have both orientations, combine a lateral trend as well as a vertical trend. So this will lead to building relatively complex proportion cubes, but these proportion cubes will be very powerful in the end to control your spatial distribution of facies, because it's basically a 3D representation of where you want your facies to be, while still giving you the latitude of running simulation. So it's not a deterministic result that you will get. So it allows you to take into account what we don't know. So the fact that you run simulations with different realizations or a multi-realization workflow, it allows you to basically get the right average, to get different realizations of that average. Of course, you can also combine any of the techniques that we have seen. So if you recall, in the initial few slides, we talked about the different facies modeling techniques. These can be combined together, and you can add proportion cubes to that to better control the facies distribution. So you could use nested simulation. You can basically use 2 different techniques, truncated Gaussian with for the EODs, for instance, and a sequential each EOD. And you can also make sure that for each simulation that you run, each facies simulation, you put in your model as much constraint as you can. And when I'm talking about constraints here, I'm talking about the interpreted boundary. So what we can see on the seismic is the geological object erosion is ending here and here. So that's a constraint that you can add to your model. You can also add to your model anisotropy with the varying channel. The sedimentary object will have elongated bodies in the direction of flow, and then narrower body when you are perpendicular to the channel axis. And then you can add the proportion cube, especially well, we talked about channel system. Again, you know, you have the sandier facies at the base and you have a fining upward sequence, or you have the levees, which are sandier closer to the channel, which is the example showing here, compared to the shalier objects, which are further away. So all of these constraints are the results of the data you have, are the results of the knowledge you have, and how you can put all of that together. I just wanted here to give a brief background on what is a proportion cube. I guess most of you know that, but I'll just make that description real quickly before I move on to showing 3 case studies and used also proportion cubes to build our reservoir models and our facies models. So proportion cube is basically a continuous field of numbers between 0 and 1, and the values that you have are representing the probability of occurrence of a given facies in a reservoir model cell. So let's say, for instance, you have a value which is 0.2 in a proportion cube for a given facies. So remember, you need 1 proportion cube per facies because you need to define the probability of occurrence for each of the facies. So that means 0.2 means you have 20% chance that facies 1 will be simulated in that cell. And if you look at it in terms of number of simulations that you run, that means 20 out of 100 models will have facies 1 defined in that cell. So it basically, what it does, the value that you have will control the spatial aspect of it. Maybe in an area of the model, you will have 80% chance for a given facies to be located, and in another area, you will have maybe 10% chance for that facies to be located. So you're basically saying to the model, okay, there is much higher chances that this facies is located in that area compared to that area. As we've said, this needs to be defined for all facies. And of course, in terms of probabilities, you need to make sure that the proportions or the chances of occurrence of each of the facies, when you sum that up, is equal to 1, because you need to fill up the whole space of the model. And after that, there's a very also interesting aspect in a proportion cube, is that when you compute the average of the values you have in the cells, so in an area, for instance, you compute the average value of the proportion cube, this average value will define the facies proportion that you will expect in the model. So it also controls the quantitative aspect of it. And this is where proportion cubes are very interesting, because you can both control the spatial aspect, so I would say the gradient or the variability of the, also control how much of a given facies you actually put overall in your model or in a given area, channel versus levee versus lobe, for instance. And that is very important, because you have the way to work in getting avoid the volume bias that we've talked about, because proportion of different facies will basically equate to volume in the end. You can control connectivity, because the more of a given facies, for instance, sandy facies you have, the more connected they have, the probability it is, so you have better communication from a dynamic simulation point of view. So that's why this is a tool that I really like to control spatial distribution. So now the will be how to translate all the information you have, the knowledge, the eyes, as we've spoken, into a proportion cube that makes sense and that will allow you to control the spatial distribution of your facies. So let's start with the first example here. On an application on offshore turbidites. Okay, so in this case, we are looking at a multi-story channel system in West Africa. So it's a passive margin object, typical turbidites. You can see there's a few faults there, and the subsurface team there had a seismic, so they have a relatively good quality inversion product here with a pseudoacoustic impedance response, which seems to make sense with regards to the interpretation of the different geobodies that you can see on the top section here. So that's really nice, and you can see that within each geobody you also have variations of that pseudo IP attribute. So the question here from the team was, okay, can we use that information to try and control facies distribution? And when we did that piece of work, we said, okay, yes, let's try and use seismic to provide some facies spatial organization. So the trick really was to say, okay, how do we translate the pseudo IP values, which is, I won't go into the units of that, but basically it's a you have a complicated elastic parameter property, but you want to make sure that this elastic parameter we saw using the wells and the data I make that talk to the proportions. How do I translate that? So what you need to do is a kind of transfer function to relate pseudo IP values to probability of occurrence of different facies. Now, it may be easy to say, but this is basically the challenging part of the work here. The transfer function is what we need to define and what we need to put our efforts in to make sure that what we are translating into facies proportion makes sense. Then you need to define proportions for each of the facies, so that's 4 times the amount, so you need 4 transfer functions. And once you have the proportion cubes, yes, you can run your stochastic simulation algorithm, look at the outputs, and you can have a kind of feedback loop if you need to adjust your transfer function. And that's typically what we've done here. So that to have something that is both trying to control quantitatively and the spatial distribution of your model. So here is on the next slide. So you will see the 4 different proportion cubes that were defined on the basis of that pseudo IP output from the seismic. And clearly the objectives of the team was to properly address geological spatial distribution aspects to make sure that it's consistent with the what was observed on the seismic. And the second point that was really important for them is to respect the proportion targets to avoid any volume biases. So you can see here that I'm highlighting with a few of the arrows the high proportion of a given facies. So the top left is the shaly facies, and you can see the green facies located in the area where you have high probabilities. You have the intermediate facies, which are the brown, and the greens, which don't have such a high contrast, but still they are located in the areas where the problem. And then finally you have the orange facies, which is the sandy facies, which are located in the area where they have highest probability of occurrence. So this allows you to build models that which are basically consistent with the data that you are using to do the seismic interpretation. The second example here is on reef platform in carbonates. So I'll start off by saying, okay, carbonates, you need the clastic environments because you could have a whole bunch of additional effects on top of just the depositional aspects. And inside the depositional aspects, we have, I would say, a large array of different environments. So it's a whole new world on itself. So in this case, what we're doing, this example show you the interpretation. So that's the first building block in that example of carbonate on a reef platform. You need to know where are the different EODs that you have. So you have an interpretation from the geophysicist and geologist trying to basically subdivide the carbonate reef into the different stages of the carbonate sequence stratigraphy. So you have the belt phase, the aggradation, and then the drowning of the reef phase. So basically you have the interpretation, which is important to understand where is the leeward, windward margins, if they can be and in addition to that, you need to know for each of the environments inside a given sequence of the carbonates, what kind of facies arrangement you are expecting, let's say inside the lagoon area, the fore reef area, the reef itself. And you know that in carbonates, usually you basically ask your sedimentologist best friend, you say, okay, can you quickly describe the different facies I have? And then he pulls up a list of 20 facies to describe, and you say, okay, stop, I need something a bit more simpler. So we do that using the calibration data, and then we try to see if the seismic can give us additional information. And typically in carbonates, what works really well is the relationship between porosity and acoustic impedance. It's not always easy to get that because you need a high quality carbonates. Sometimes this makes it difficult. You have more multiple effects also, or even internal multiples, which can make it difficult. But sometimes we do have an information that we can use to do that, maybe just as a soft trend indication. And in this case, we had seen that, yes, there is information and there is a spatial distribution to acoustic impedance. So we tried to relate that with porosity and to the different facies that we had. So in the end, we could find a kind of soft little loose trend that we wanted to integrate. So, example with the integration of, well, interpretation, and the wells, of course, the acoustic impedance, so the seismic data that we had, knowledge, the geological knowledge on the different EOD maps, environmental of depot, the rock type proportions that you would expect, and the arrangement of facies that you would expect in each of them. After that, you add some other constraints that you can in the modeling, and then you get a model which integrates all of that into its output and its facies model output. And again, you can see that most of the effort here has gone into the facies modeling. And I'm not showing you the petrophysical modeling because the petrophysical modeling was relatively straightforward in that case, because each of the facies, each of the rock type had a defined set of petrophysical parameters. And then the next step was just modeling or simulating the petrophysical parameter distributions in each of the facies before going into reservoir simulation. The last example I want to show you here is dynamic integration case. So I want to show you here, again, a turbidite environment. In that case, we didn't have, I would say, very good eyes. The seismic was relatively poor in that interval. We had iso-impedant sands, but we had some good well information. Particularly in that well, we had more sand at the base and less sand at the top. So we tried to represent that with a vertical proportion curve that you can see here on the left-hand side. So that's fine. And then we needed to match a DST, so a well test, to make sure that the model that we are building is consistent with the dynamic data we had from that reservoir interval. And you can see here that the black line that we have, well, is not quite matching with the historical data. So what we tried to do first is we said, okay, we're lacking maybe a bit of continuity. Let's try to increase the variogram range in the model and have better connected, actually better matching the data, especially that first stabilization. But then again, at 10 hours, you can see that there is still that change of behavior, which is not satisfactory. So what we did is we tried to change the facies aspect of that bottom interval, because this is where the DST was acquired. So we tried to use increase the connectivity greatly to see if that impacts the simulation model. And you will see in the next slide that actually we did 5 iterations on the model to actually reach a satisfactory match. And you can see here that the bulk of the work was done on the facies model and not on tweaking the dynamic parameters or semi-analytical with the pi or sapphire to match the DST. Here we wanted to that the facies distribution in the model was actually satisfactory to match the test, and hence we would know that the simulations and volumes that we would get out of the model are consistent with the dynamic data and hence more accurate with regards to reality compared to something which is not matched. So in the end, what we noticed is that we probably needed to put more sand in the base of the reservoir interval to reach a satisfactory match. So I'll show you that we increased the vertical proportion curve. So we changed the proportion cube to make sure that the probability of occurrence of sands is higher at the base of the reservoir. And once we've done that, we also increased the variogram range. We kept at what we had. And once we've done that, we basically were able to get a very satisfactory match between the model and the data. So, and that's both on the derivative and also on the pressure buildup aspects. So and I hope now everyone is convinced that facies modeling is a key step in the modeling workflow. It's not the only one. It's not the most important one, but it's a key step, as are other steps in the modeling workflow. And I would say the key word here is integration of all the available data that you have, along with the geological knowledge, to make sure that we are consistent across the board and to have as robust models as possible. Sometimes you will have a piece of data that, well, is bothering you, and we usually choose in terms of acquisition. We need to try and look at all the data and make sure everything makes sense on our end. That's really, I would say, our core job here. Third point is that this controls the spatial distribution of petrophysical values, as we've seen. So you have the impact on the volume, you have the impact on the fluid flow simulation. So this is really an important piece of information inside your model to make sure that the forecasts we do are correct. But to do that, we need to, in everything we do in building models, is to make sure that we translate everything we know correctly into the model. And here I must say that we all need to have the basic tools, the mathematics, the statistics that are essential to do that kind of translation work correct. There is also room for innovation in that aspect, because this is where we have the largest freedom in combining techniques, using additional constraints, integrating seismic with geological knowledge, with the dynamic data, and make sure that all of that data is making sense together to get us to have a best robust model that we have. And this is where a lot of the innovation can actually take place, because every field is different. Every time you have a different set of data, and every time you have to have the I would say the imaginative work of trying to combine all of these data pieces together to make good sense out of them. Lastly, I just want to say it's one piece of the puzzle, and it's not the only piece of the puzzle. You still have very important aspects, which are the dynamic data, the PVT, relative permeabilities, and other aspects to make sure that we are robust across the board. And now I can tell you, and you know, why I care about facies modeling and the spatial distribution of facies. So I would like to thank again NAPE. Thanks everyone for attending the presentation, and I'll be happy to attend any questions you have.
Okay, thank you very, very much, Eric. Back to you, the chairman, Mr. Bioda Desoya. Mr. Biodun.
Okay, thank you very much, Eric. I was trying to get myself unmuted. That was a very, very good presentation. It's pretty clear that we have to care about facies modeling more than ever before. It's a very powerful tool. It explains quite a lot of things as to the successes and sometimes surprises that we see when we drill and when we explore and do all the work we do. Let me just quickly summarize as best as I can, and I must openly admit this is not my core competence area at the moment, but I have people who are very vast in this area working in our office. You started off by saying that you know, reservoir modeling is akin to weather forecast. You try to give us something about weather, and you draw some analogy with that, and then facies modeling versus petrophysical modeling is key. To, you know, we have to put this in context. Now, the modeling is used for what? Is used for production forecast. It's used for decision making. Decision making in terms of whether you want to invest in an asset, investment, divestment, etc. It also tells you where we want to drill. And the key prerequisite is the quality of your data. One of your key data sets you need is your seismic data. Your seismic data has to be good quality. It has to be specially acquired to focused seismic acquisition to give you sort of a kind of result that will enable you to do all of this. So you need good quality acquisition to work. I'm pretty sure you need good quality well logs as well. And then the requirements will be seismic. You have geological outcrops, if you can, just so that you can have the analogies and see examples, basin models, ancient or current analogs, outcrops for predictability, development scenarios. It's also very important that then you went on to speak about the techniques that you use, the kriging method and all the other ones. On the petrophysical modeling, what is key here is the net to gross, porosity, permeability, etc. And you have to have good eyes on your seismic, that is key. And then you have to have knowledge, and then you begin to arrange your various processes that you go through. The impact on spatial distribution, you mentioned that. You need dedicated seismic, like I said, you need to have a controlled processing. So it has to be carefully processed, carefully acquired. And then seismic characterization is very key, part of the process that you follow. Then you went on to cover the spatial distribution. And you mentioned there that knowledge of small-scale heterogeneities is key. Knowledge of large-scale heterogeneities is key. And then you have knowledge of geometric Facies, geometric geometry is very key. So we have a fair play. You have sequence boundary, flooding surfaces, erosional surfaces, and stuff like that to guide you in that. Then you spoke about bridging the gap between naturalist world and numerical world, and this is where the numbers and the algorithms become very important. You spoke about the heterogeneity of reservoir properties and how that supports Facies modeling. Then you spoke about how you go about the steps. So you spoke about proportion cubes. These are reliable. And you started with 1D, 2D, and 3D models, and how the models will all add up to 1. You have 0 to 1 for the proportion cubes. And then the probability of occurrence, and then the proportion cubes needs to be defined for all Facies. So you have to do that in all cases in order to get the expected result. And then you concluded by saying that, well, you gave us applications examples. You had the West African margin example, passive margin example of a turbidite clay. And then you showed us also the carbonate example. And then you came back to another, you gave us an example of a dynamic integration. The carbonate one was a reef platform. And then in the case of the dynamic integration, it wasn't as good quality seismic and all of that. So in all, you concluded by giving us some key takeaway points. And you said that Facies modeling is key. It's a key step in modeling out workflow. In the modeling workflow, integration of available data and geological knowledge essential for producing consistent and robust models. You said that control spatial distribution of petrophysical values impact on HCIP, impact fluid flow simulation, need to bridge the gap between naturalist world and numerical world. Production cubes are great tools, and the mathematics and statistics are essential for translation. Then you have combining techniques and integration of different data types and skills offer room for innovation. And you, the final point you made was that the Facies modeling is just one piece of the puzzle. There are still other modeling you have to do to have the fuller and complete picture. I don't know if I did a good job at that summary, but that's what I've been able to capture. I will now leave the floor for questions. I believe we have a couple of questions. I'm just going to scan through them and read. I believe everybody that asked a question do have their names here, which is the standard procedure. The first one on top, which may not necessarily be the first one that came, is from Taiwo Afuye. But before I go into the questions, I think we should just, in our individual Zoom meeting ways, let's just say a very good, give a round of applause for Eric for a job well done, and to thank him for sharing this knowledge with us. I believe that the paper is well taken, and we will apply the knowledge learned in daily work as explorationists, and it will enhance and improve the quality of our output. So thank you very much, Eric, for that paper. Let me go to the questions then. So I was, sorry, I have, I'm trying to read all the questions. Latif, I don't know if you could help me here. I'm trying to, okay, good. Sorry, so I'll just
okay. I can help run through the questions.
Right. Please.
All right. So Eric, again, like Mr. Our chairman, Mr. Abiodun Adesoya, fellow of NAPE and past president, I just said, thank you very much for your presentation. It was highly enlightening. I'm not going to go into the summary again. So we have Cornina Ale. Our question is very straightforward. Channel on your slide 10, the channel was distinct. How did you establish the boundary and the extent of the channel in the reservoir with limited well penetration? So I guess she's referring to the models you had shown on slide 10. Did you get that, Eric?
Yes. Okay. Yes, I got that. I would say if you don't have a lot of well, your joker is the seismic data, to emphasize on the seismic aspect. With very good eyes, you can actually define the boundaries of the large-scale geobodies, and typically that's the channel you are mentioning here. So in addition to the wells, and typically in passive motor field, our managers, it's a high capital intensive, I would say, areas where drilling a well is very costly. So what you can do here to have better eyes is basically invest in your seismic, and with your seismic try to focus on the parameters that would allow you to see the different heterogeneities at large scale, the geobodies. And in that case, this is how the well boundaries, the channel boundaries were defined. Of course, it's much better than trying to drill a bunch of wells in that environment. It's much more cost effective to have a high quality seismic because one, it will allow you to drill in the right place the next time, and secondly, to also
okay,
the more robust model. So the
key
here is
you lost your
seismic.
video. Sorry, we lost your audio for about a minute. So you just want to back up just a minute.
Yeah, sorry about that. What I was trying to say here, the key in deep water environments where we are relatively capital intensive is seismic, because that will allow you to see geobody boundaries, such as the channel ones, rather than trying to drill more wells, which would be much more costly. So seismic is the key aspect, and it's a much more cost-effective aspect, in particular in deep water environments where we usually have our turbidite plays. I hope that went through, Latif.
Yes, every bit of it went through, and actually it sets the stage for the next question.
All right, great.
This is from Mr. Victor Agba Davies. He's a fellow of NAPE. His question is pretty short. In addition to seismic, how much core data and well data was used in this reservoir study?
Well, I'm not sure which reservoir study he is referring to, but I can make a comment, I would say globally, on core and well data. Yes, so of course, I'm talking about facies here as though the facies information is something we acquire. Facies is something we interpret, and we usually interpret that from the well data and from the core data that we have of that. Usually when you are in an area that you don't know, you would probably want to acquire more core data to make sure that we have physical measurements of the rocks themselves. And there is two aspects to the core data. The first one would be the I would say sedimentological aspect, so the facies aspect of it, as well as the classical or the convexity. So that allows us to calibrate well information and make sure that the relationship between facies information and petrophysical information is correct. So that's really key. But in addition to that, something that we haven't spoke about, we have all the special core analysis aspect, which is basically the relative permeabilities, the MICP, so the saturation laws that we can get out of that. And all of that is more related to the, I would say, dynamic simulation, which is as important. So in an area, let's say, okay, we know, okay, Total is relatively present in the shelf area as well as in the deep water environment. When you start having fields which are next to each other and you can see that you have a general trend of the data, maybe when you're trying to go for the next field, for the next exploration well, or the next development in a similar environment, similar age of rocks, etc., you would probably need less and less I would say information, because you have very good analogs to work with. So it really depends at what stage of the development area and you are trying to develop a new field, you can, keeping in mind the project economics, of course.
Mm-hmm. Mm-hmm. Just one quick question, similarly tied to that. The fact that you need good quality seismic to be able to do your modeling, to build the Facies modeling and all, will it be an absolute truth in saying that in such an area, there must have been, you can't go from an area that is that doesn't have 3D seismic, or that is having a first time 3D seismic? Because when you're having your first time 3D seismic over an area, the chances are that there are quite a lot of unknowns. There are a lot of things, orientation, even the acquisition parameters may not have been fine-tuned to give you the desired results. Now, because you need a controlled seismic, you need a good quality seismic, you want to process the data to enhance all the features, all the elements on the seismic that will enable you to do the work you want to do. Will it be out of place to say, therefore, that you don't get to do this sort of serious stuff on your first seismic acquired in an area? You have to come back again. If you acquire a streamer seismic, maybe it has a lot of noise on it, you might start thinking of an OBC or nodal seismic and stuff like that, that will give you a better quality output.
So absolutely, you're right. There's an E&P cycle that we need to, when you were going into a virgin area, yes, the first thing, I mean, even back at the times, we would drill wells on 2D seismic lines, and you would search for any anticlinal object. When you have a structure on structural aspects, you would drill based on that. Today, the structures that we have left, and I would say the objects that we have left most of the time, are more complex seismic, but as you said, there's a lot of unknowns. So you would try to get the best out of your seismic initially. And here we are much more in an exploration phase of the E&P cycle. And in the exploration phase, what you would try to want, it's, if I can make an analogy with I would say tool developments or software development, you want a proof of concept. You want to make sure that the area where you have hydrocarbons, hydrocarbon accumulations in large enough quantities for them to be commercial. So that would be the first objective that you have. You're not trying to make the aim here that are, I would say, much higher capital intensive than the single well exploration well or 2 exploration wells that you want to drill. So you are right. So you would start off with, I would say, small, trying to prove that you have hydrocarbon accumulations. Once you have that, depending on the sizing, the appraisal program that you would need to do for that, either you would go for a second seismic vintage, because the next step you would say, okay, I want to develop that object, but I can't really see what is the detail inside the reservoir. So yes, you would probably want to go with the second phase of seismic acquisition, either OBN, OBC, whichever is suitable to characterize just one well that give you information on the rocks themselves. Maybe not a core in the first well, but at least you have the logs, you have the hydrocarbon column, if you have some resistivity in these logs, etc., etc. So you will want to, I would say, fine-tune that on the basis of the accumulation size, etc., etc., and the potential development.
Okay.
Sometimes streamer acquisitions are enough. You would just need to reprocess it on the basis of the additional information you get from the logs. Maybe you have sonic data, a VSP, that allows you to better grasp the parameters for processing and imaging. Environment, then you would probably want to go in OBN if you need that for reservoir. If you need that for reservoir characterization.
Yeah.
All right. So let me just again jump in. Permission, my chairman. So I'm going to lump like 2-3 questions that essentially are similar. So the first one is by Valentine Uwoche. What do you advise when we are faced with challenges of not having good eyes, which means not having good seismic, or reservoir is not within tuning thickness, and we have limited wells drilled to capture the reservoir heterogeneity? So that's Valentine. Hold on. We'll wrap that up with another question that is similar or close. Thank you for the presentation. My name is Joy Obakeye. What Facies model have you adopted? And is there a regulation that guides the drilling process? So it's really the first part, your adoption of the Facies model. And then from David, how does variation in vertical proportion curves affect a more representative Facies model in deepwater turbidite? So I tried to capture all the heterogeneity type questions in one.
Okay.
Are you there, Eric?
I'll try to go through those. I'm here.
Okay.
Can you hear me?
Loud and clear.
Okay. So the first question from Valentine is, what do you do when you don't have good eyes? So I would say first things, if you have a seismic and it's an old, many examples where reprocessing data, especially if the vintage is 5 to 10 years old, processing techniques and I would say data processing techniques in processing contractors or even velocity model building, so imaging techniques have really evolved a lot recently. So the first thing I would say is try to change your eyes. If you have a seismic data, try to reprocess it. I would say that's the first step. If you don't have the possibility to reprocess it, or the reprocessing is not good, and you have well data, well, I would say, yes, rely on your wells if you can. I mean, I'm not sure your management will allow you to drill wells just to know where your facies is located. That probably this, and this is where the knowledge part would come in. So you would have to apply your concepts and try to make sure that the concepts that you're applying are consistent with the data you have. I would say the less data you have, the more freedom you have in terms of applying different concepts, but that also means that the larger is the uncertainty. And as I've said initially, our jobs as geoscientists is really to highlight the uncertainty and the associated risks. So if you think there is a lot of risks living with the situation that you are in, and that for the company this could create capital expenses with no return, let's say a dry well or development wells which are not correctly positioned, then maybe that's where you need to have your voice heard in saying, okay, we could invest in a new seismic that could allow us to invest our capital in a much more robust or higher return on that. So that's the point on when you don't have good seismic or good eyes. The second question, I think, was on facies. If there is any specific facies guide or rule to apply, if I'm not mistaken.
Exactly.
I would say here you need to adapt to the context in which you are. Either you are in a context where you have turbidites, for instance, or even I would say a fluvial system. Then what I would say, you need to adapt your facies modeling rules to the depositional system that you are trying to work with. So of course, it's really important to know in which depositional system you are. And I know of an example in particular in the North Sea, where the well was first interpreted as a deepwater fan initially, and ended up being reinterpreted into a fluvial system, and which, well, of course, with the concept that you apply to your facies modeling would be quite different. So it has had a large impact on that. And this was a debate between sedimentologists. So I would say you need to adapt to the different depositional system. And this is where knowledge, concept of the depositional system and knowledge of the numerical world is important, because you would need to bridge that gap between the two. So there is no general rule. I would adapt to the depositional system that you are and make sure that quantitatively and qualitatively, or at least spatial distribution, is consistent with that depositional environment. The last point was regarding the vertical proportion curves. Is that I didn't quite really catch the question, Latif. I think if it had an impact on the turbidite environments.
So the question was, how does variation in vertical proportion curves affect a representative Facies model in deepwater turbidite?
Oh.
And that was by David Anamnese.
All right. Thanks for the question, David. So in here, I would say a vertical proportion curve is usually trying to represent the vertical arrangement of the different facies. And we know that in turbidite environments, you start off with the erosional event in the channel system. Of course, you have unitary channels. Normally, the different unitary depositional systems, it's very rare to be able to image those. So your VPC should try to represent the overall trend. And it has a very important aspect, and I can relate to another project we worked on, where if you didn't use a VPC and you try to disperse the facies model inside the channel, the end result was not enough connectivity, so you couldn't match the DST, and it didn't match the DST, and you couldn't actually produce from the reservoir with the development scheme that you that was planned. And by using the VPC and making sure that the basal sand, that was the massive sands of the turbidite, was continuous enough, then we were able to match the well test, and we were able to have a comprehensive production from the well scheme that was related to that reservoir layer. So it can have a large impact on the outcome of the forecast that you are providing, as long as it makes sense and it integrates with the rest of the data set. It's one of the powerful tools that we can use, at least in turbidite environments.
Okay, Latif, can I just quickly, I'm looking at the time. We have this 12:34, we have about 26 minutes, and the NAPE also have certain protocols they will need to follow. Couple of other
Exactly.
additional questions, and I will just need a very quick answers to them. One is by Yemi Shoroye, and he says, you mentioned adaptive acquisition and processing between the VO and the V0 and V1 maps. He would like to know the special processing parameters used, especially in preserving true amplitudes or direct hydrocarbon indicators. That's one question. Another question is from Sheyi Obafemi. How do you validate a model and quantify the uncertainties associated with it? Does process-based rule-based modeling, I don't understand, does process-based rule based on modeling have any edge over the conventional geostatistical approach you highlighted? Then 3, do you use well information to determine the properties of the facies in the proportion cube? And then the last one, which I have, is Juliana. Okay, no, I'll go to Taiwo Afuye. The question is, how is this robust geologic facies model correlates well with porosity, permeability, cross plots on a QC approach? And then Obasui, final one, can the future of performance, static and dynamic behavior of the field be predicted from the model results? I think those are the questions I'm able to capture. I don't know if you could get them in a few minutes, please.
Yes, all right. I'll try to address them. So I'll first start with the V1 versus V0 aspects with the adapted seismic acquisition. Exactly. So I don't have, I mean, there is no single set of adapted seismic acquisition parameters or processing parameters that would give you the best image. What I would say is that the best way of addressing that is to make sure that there is discussion, or at least integration of the asset teams, the people that actually need the result of that processing, what they need. And you mentioned amplitude preservation, DHI, etc. So all of these are really important, and make sure that the asset people, the end client, talks to the processing supervisors and also to the contractor. The more their communication there is between the three, the less chances there is that there is a glitch in the processing. And I would say the higher the chances of making sure that the processing, and the imaging addresses the challenge of the asset. But I wouldn't say there is a given set of parameters. The reason was you had a classical streamer, and afterwards it was a large bandwidth streamer. So it was a broadband that was acquired. And so you had a much better low frequency and much better inverted properties afterwards. That's, I would say, the main reason. The second question was related to, I think you had the uncertainty aspect.
Yes.
If I recall correctly. You're right. It's difficult when we build a model, especially if we don't have dynamic data, it's difficult to validate a model. And then you have the uncertainties that you have. I would say the key is making sure the data together are consistent across the board. So if you have well data, you have core data, you have dynamic data, well test, for instance, you need to make sure that all of these data are consistent together. And as we have seen, making sure your model, when you try to simulate or replicate the DST, is correct. The validity of a model is basically when you drill a well and you find the sands in the right place. This is how you validate a model, is by taking the risk of actually doing something is by doing the operations you are envisaging afterwards. So by drilling an exploration well, if you're at exploration stage, but usually we don't have models for that. So drilling a development well, producing from that development wells, and making sure your model, the forecast that you have done, is actually suitable. This is how you validate models. You can also, one technique to validate a model, which is really interesting, is 4D monitoring, because you could see the quality 4D and probably then adapt your model to make sure that what you see in 4D, which are the changes, are consistent with what the model is simulating. That's a really interesting solution, because you're not drilling a well. So, and you can repeat it as well to see how it evolves in the future. Process-based modeling, yes, it's very interesting. The difficulty here are the constraints usually, and the quantitative approach. And the techniques I have seen so far, you have very geological outputs from the algorithms that do process-based or rule-based modeling, sometimes to constraints or to respect quantitative proportions. But that's a very good approach if you can constrain it with some of the parameters or bits and pieces of the seismic whenever you can see a unitary channel, for instance. So I would say, yes, it's something worth looking into. It does have, I would say, a complicated set of parameterization that you need to work with. So that's I would say, the downfall of it. There's a lot of numerical aspects and algorithm aspects in it that usually doesn't make it very user-friendly, but for those who can manage that, that's fine. Do we use well information to determine the proportion of facies? Yes, but with a small warning. Yes, but make sure it's consistent with the knowledge you have. So if, for instance, you know that in a channel system, we know that we have a higher sand proportion in the core of the channel and the axis, and you have probably siltier and shalier facies on the edge. Let's say, for instance, your well actually was on the edge of the channel, and you just have a small sand interval. Just make sure that it's still consistent with the knowledge you have of a typical width and thickness of that channel, if that makes sense to use that proportion. So you could sometime overrule the well information with knowledge if this is more suitable.
All right. So
I think.
Okay, can you hear me?
Yeah.
All right. So we have a ton of questions.
Yes, I can hear you.
We've overrun our slot by about 5 minutes. So this is the point in which I need to first send my appreciation to everybody that's brought in a question. For those individuals who couldn't answer their questions, from Daniel Omoshowafa to David again, Anonese, to Lulope Obishason, Prince Eko Kotu, Ikechukwu Obodu, Sonny Eze, Elijah Njoku, Chinotu, even my General Secretary, Mr. Emmanuel Ebele, and even the others that asked questions. We do apologize. We will see what we can do about attending to your questions offline. But again, thank you for taking the time. I don't know if we still have our chairman there. Mr. Chairman, are you there? Okay. If he's not there, this is the point in which we say thank you, Eric. It's been exciting. We have a lot of people still asking questions. What we'll do, like I said, is we'll see if we can attend to those questions offline. At this point, we would like to invite the representative for Total to give the sponsor's remark. This is the Executive General Manager. Hello, sir. Okay, as I was saying, the Executive General Manager, Deepwater, Geophysical and GSR, and Planning, Total Exploration and Production. Mr. Olatuji Akiwumi, welcome to the show. Can you hear us loud and clear?
Okay, good afternoon. Good afternoon, everybody. Thank you, NAPE. Thank you also very much, Eric, for that great presentation. And thank you for giving us the opportunity to sponsor this webinar. I'm representing my managing director, Mr. Mike Sangster, who is not able to join us, but he has asked me to read this speech. The President, Nigerian Association of Petroleum Explorationists, distinguished fellows of NAPE, gentlemen of the press, distinguished ladies and gentlemen. Total is greatly honored to be the sponsor and host of this month's technical meeting of the Nigerian Association of Explorationists, NAPE. Total has proudly been an important partner in the monthly presentations of NAPE over the years, just as we have with the annual international conference of. The company truly believes that this monthly technical meeting is not about the professional development of NAPE members, some of whom, many indeed of whom are Total staff, also provides a vital platform for professionals and industry operators which will benefit the industry and the country at large. As a body of explorationists, you, like every keen observer of the industry, should be concerned that as we deplete our oil and gas reserves as a nation, there are no proportionate exploration activities to ensure long-term sustainability and replenishment of the resource that accounts for more than 90% of the country's foreign exchange earnings. A combination of factors which include uncertain fiscal and regulatory regimes, policies that make new investments unattractive and uncompetitive, low oil prices, much more, are easily to blame for this development. Total, as a key stakeholder in the Nigerian oil and gas industry, is prepared to work with the government partners, stakeholders like yourselves, to address these bottlenecks to new exploration investments. I expect that this session has also been able to focus on some of these issues, even if this is not the topic of today's technical meeting. This said, we are all aware of the raging COVID-19 pandemic, which has held the world hostage for several months now. The adverse effect on lives and businesses, especially the oil and gas industry, cannot be overemphasized. Please permit us to touch on some of Total's interventions in the fight against the COVID-19 pandemic. As a socially responsible company, Total rose to the clarion call of the federal government along with its partners, led by the NNPC, by contributing to a donation of 21 billion naira in support of the federal government's COVID-19 efforts. Total's contribution was $3.2 million, equivalent of $1.2 billion. The company also supported the Lagos state government with critical supplies and medical equipment. In Rivers State, we reached out to our stakeholders by providing medical supplies and support for our host communities and the state government. Our downstream company, Total Nigeria PLC, donated 50 million naira as part of a combined contribution with the Major Oil Marketers Association of Nigeria, MOMAN, under the auspices of the NNPC, and provided the Lagos state government with fuel for logistical support during the pandemic. Nigeria is crucial to the Total Group, accounting for around 10% of its equity production. Total has also invested approximately $10 billion in the country in recent years. Beyond these direct investments, we continue to contribute in several ways to Nigeria's economic development through our CSR initiatives and collaboration with professional bodies such as yourselves. The NMGS Total Prize has been the coveted prize of the society for years, because in addition to money award, winners go on a fully sponsored technical trip to our scientific center in France for 2 weeks, during which they are exposed to our proprietary exploration technologies. The company makes an annual expenditure of over $40 million on corporate social responsibility in Nigeria, with remarkable investments in capacity development, employability, health, education, as well as infrastructure development. Some of these you may have heard of. They include the Institute of Petroleum Studies, which was established in 2003 and offers world-class education on industry-oriented training, continuing education, applied research, capacity building, and community service to meet technological advances in the oil and gas industry. The MIT Empowering the Teacher, MIT ETT program, enables outstanding young Nigerian lecturers in the area of science and engineering to collaborate with the Massachusetts Institute of Technology, MIT, in developing new curriculum and teaching methods that adopt MIT's emphasis on problem solving and developing entrepreneurial attitudes among students. Benefiting lecturers have been able to implement innovative programs in their universities in Nigeria. Last year, we commissioned more than 14 legacy projects, including mammography centers and maternal child referral centers. As we speak, arrangements are in top gear for the commissioning and handing over of the newly completed projects to benefiting communities across the length and breadth of the country. As I conclude this speech, it is important to look ahead to a post-COVID-19 world. Our experience during this pandemic has shown that some of the adaptations and innovations brought about by this scourge will remain with us for a long time, if not indefinitely. The deployment of teleworking and virtual meetings like the one we're having now have become the new normal. These will have implications on the investment strategies and imperatives for business and even governments around the world. NAPE should adapt to a post-coronavirus world and seek ways of reinventing itself for the purpose of continued relevance. I have no doubt that the respectable membership of this body will take advantage of this month's presentation to make deliberate, robust, and incisive contributions aimed at addressing the many challenges confronting our industry and nation. Thank you very much for your attention. And once again, I wish to thank you for the opportunity that you have given to us. Thank you very much.
Thank you.
Thank you.
Over to you, Mr. President.
Okay, good afternoon, everyone.
Good afternoon.
I'm expected to give vote of thanks, but just before I do that, I want to just mention some very important points of note. The presentation of today is very significant. The chairman of today is ex-Total. The president of NAPE was trained by Total some 30 years ago under the leadership of late Professor Kingsley Ojo of blessed memory. The speaker for today is a complete gentleman with a very rich profile. The topic is timely. The sponsor of today, I want to repeat, trained the current president of NAPE 30 years ago. It's a fantastic combination. I'm excited to be the one giving this vote of thanks. And I want to sincerely extend the appreciation of the NAPE executive and the entire membership for this wonderful sponsorship. We didn't expect less than what we've had because Eric was sharing from his personal experiences, not what he read from books. He has been a co-inventor. Eric, we're very grateful to you for sharing this rich understanding of the geological model, Facies modeling, and why we should care. As a Westside geologist, without some of these office advices and guidance, the biggest mess any Westside geologist will face is to drill a dry hole. Your job is so important to the Westside geologists. That is my own area. My brother and friend, Mr. Tunji Akinwumi, I'm glad you've been asked to give the sponsor's remark at this event. We're excited. These programs have been on to keep our members busy. We didn't expect less than what we've had. There's no better time hearing so much about risk-related issues in the industry that will help to save costs. NAPE will continue to partner with Total. I'm happy I saw a lot of even my mentors in those 30 years back, part of the participants of this event. We are so glad. We appreciate the Public Secretary of NAPE with the media team. Every participant that made time to be part of the success of today's event. Eric, I want you to know that we had about 350 participants globally, in spite of all the challenges and the tight schedules. That's a wonderful turnout. We appreciate the staff of the Secretariat of NAPE who work day and night to make sure events of this nature are sustained. We are not going to cancel any events. NAPE will sustain all the events for the year. In fact, tomorrow we are going to be hosting the Minister of State for Petroleum Resources. We want to invite each and every one to join us to listen to the Minister tomorrow from 11. Once again, on behalf of the NAPE Executive, we thank the Speaker, Eric, the sponsors, the chairman of today's event for making time to be with us, a distinguished fellow of the association and a past president, and one of my mentors. Thank you very much. I appreciate your time. God bless.
All right, thank you, Mr. President. And thank you, Mr. Olatunji Akinwumi. Thank you, Chairman, Mr. Abiodun, and thank you, Eric. We now have to move to the next level, which is the announcement. So at this point, we want to take on some very key announcements of the association. So the first announcement that we will start with will be for our main events for the year. You know, and I wonder if the P is still around. I would like our video to also show while this is going on. My President-elect, I hope you are there. Because this is your big baby. All right. Would you like to say a word or two about this though?
Yes, I will. Thank you very much, my Honorable Publicity Secretary. Folks, we are gradually getting to the big show, the big masquerade of our event for 2020. And that will be our virtual conference. I am grateful to the Total's MD for acknowledging that we are in different times now, and NAPE has to reinvent herself. We have already started that journey by moving our conference and the exhibition and the field school, everything virtual. So please go to the conference website. It's www.conference@nape.org. We've also invented in the way that we've slashed registration so that everyone can participate. I guarantee you it's going to be a very, very successful outing. I look forward to seeing all of you, listening to the over 100 papers that have been selected in both poster and talk formats. We are expecting over 63 exhibitors. Thank you to all our exhibitors who have already reserved their slots and are making payments. I actually want to thank Total. They were first off the block. Thank you so much for believing in us. We also have all our companies, our corporate sponsors, our employers. We know you're going to exhibit or you're going to advertise or do one thing in one form or shape or the other. And our pricing has actually reflected the fact that we are virtual. So please take advantage of that. We are going to have a management session, the pre-conference workshop. I am very excited about the pre-conference field trip. It's going to be first of its kind in Nigeria, being put together by Nigerians. Please watch that space. Thank you. I give it back to you, Latif.
Oh, thank you very much, Ma. Thank you so much. I'm sure we all cannot wait to see what you have in store for all of us.
Yeah. Man. Okay. I don't know.
Okay, so it's now my pleasure to also, it's my distinct pleasure to talk about what we are going to be doing tomorrow. We'll be inviting the primary steward of the oil and gas industry, and no other person than the Minister of State, Petroleum Resources, the Honorable Minister of State for Petroleum Resources of Nigeria, Chief Timipre Silva is our guest speaker tomorrow. We'll all be here for the August edition of the Nigerian Association of Petroleum Explorationists webinar series, August edition. The topic is physical regime design, government revenues, and investors' interest in Nigeria in oil and gas, in the oil and gas sector. Time is 11 a.m. and this is being sponsored by Damata Nigeria Limited. If you have not registered already, just go to NAPE webinar. That's our short link. Go to any of our online platforms. There's a lot of information on how to be part of this very significant webinar series, where we'll have one-on-one, get into the mind of the minister, understand what is driving the policies on ground, understand what the plan is for the industry, and how we all collectively can recover from the pandemic as it is right now. Again, the NAPE webinar is happening tomorrow. Okay, so next, I think I'll have to invite the president. I'm looking for Madam Nolly, but I can't find her, so I'll invite the president again. My president, are you there? Mr. President, can you hear me, sir?
Yes, please.
Okay, so the chairperson for the electoral committee was with us, and I don't know whether it's a technical thing, but we cannot see her anymore. So I'll have to hand over the presentation of the candidates to you. So over to you, sir. I don't know whether you can see the slide on the screen.
Yeah, can you scroll it?
Okay, sir.
Once again, we're in the election year, the most important election year of NAPE. So many positions going to be vacant by November. Voting will be commencing end of this month, as soon as we get into September. In the absence of the chairperson, the electoral committee, Madam Noni, I want to take it up from here. We have the position of the vice president. We have two candidates for this position. Their pictures are here. Fantastic gentlemen. Please read what they have promised to do. Go through NAPE site, check their profiles, and please, once the voting commences, please make a choice. NAPE elections are online. You can sleep in your bedroom and vote. Please, the next positions, President-elect, these are the gentlemen that are in for the position of president later on by next year. We have Elliot Tibia, we have Dr. James Edets. Please read through their contributions, what they promised to do, their manifestos. And once the voting commences, please cast your votes. NAPE elections are online. The General Secretary position is also open for contests. The candidates we have Emeka Ejika and Charles Otogile. Please read through their manifestos, take a look at their profiles, and cast your vote once the voting starts. Voting is strictly online. Thank you. Next, Assistant General Secretary. Vacant too. In November, we have Nonye Folabi and Olani Ojo. Please read their manifestos, check what they have promised to do when elected. Please, once voting commences, cast your vote. Next, the post of treasurer, the exchequer, very sensitive position. We have about 3 candidates, very sensitive position, 3 candidates, a lady and 2 gentlemen. Please read their manifestos. Once the voting commences, cast your vote for who you think will be able to take care of NAPE funds among the 3. Thanks. Financial Secretary. We have Kehinde Olafirayin and Mascot Ogunjemil. Please read the manifestos, check their profiles. Once the voting commences, go ahead and cast your vote. Thank you very much. Editor-in-Chief is unopposed. The current Editor-in-Chief will continue, but he has to be voted. Just cast your votes for him and let him continue with the good work he's already carrying on. The person that will assist the Editor-in-Chief will also, the position will be vacant by November. We have about 3 candidates as well. We have Vicky Okori, we have Princeton Dean, we have Aaron Aoduson. Please read the manifestos, check their profiles, and make a decision. We love this very serious level of participation. Go ahead. Public Secretary, the person that will take over from our President Lateef Amodu, the man anchoring this program. We have Adekunle Shofolabo and Tumbosun Afolaya. Please read the manifestos, check their profiles, and make a decision when voting commences. Thank you. Next. Okay, that is the last. Please, we want to encourage each and every one to try and cast their votes. You must pay your dues and encourage your supporters that you are expecting to vote you into office to pay their dues, without which they won't be able to cast their votes. 38th conference will be still coming up. This time around, it will be virtual. We want to use all these platforms to continue to carry out rehearsals like we've been doing. It promised to be great. It's going to be quite great. I want each and every one to register to be a part of history. The first time NAPE will be running an international conference virtually with participants from all over the world. You can't afford to miss out. This is the timetable for elections. Please go to NAPE website, take a look at it. Voting will commence from August and it will end mid-October.
All right.
Voting will commence within August, end of August. For the whole of September, we'll be voting till mid of October. So voting will be 1.5 months. Thank you.
All right. Thank you very much, sir. Thank you so much. I think this is the end of the program. Any final words, my president, to say thank you to the audience? We've finished.
Okay, once again, we're Thank you once again for your time. Each and every one that is making time to be a part of history that has been made today. We are going to sustain our programs for the rest of the year. Nothing will be canceled. We want to use technology and to move with the technology to see how we can weather the storm. NAPE, if we were a bird, we're supposed to be eagle. We continue to weather the storm. Yes, I'm quoting the director of DP. Yes, thank you very much. Please, we appreciate, we're not taking any of your sacrifices for granted. We thank Eric, thank the sponsors, thank the chairman for today, Amodo and his team, our staff at the Secretariat once again, and all participants. We talk to you, this today will have been a wasted day for us. We appreciate each and every one. Thank you, have a blessed day and a memorable week ahead. Remember to join us tomorrow.
Thank you, everybody. Have a lovely, lovely day. All right, that's the end.